Hello everyone, you're welcome to God Academy. In this lesson, I'll take you through order relations. In our previous lessons, we've gone through the different number systems and also we've explored the properties of number systems. So in this video, we are going to look at reflexive, symmetric, antisymmetric, and transitive properties of relations. Please watch this video to the end so you understand every concept. And this is the first time you are visiting this channel. Kindly subscribe so that you get full understanding of the course. In this video, at the end of the video, what you achieve is that you'll be able to classify whether a relation is equivalence relation or is an order relation. Again, you'll be able to check whether a relation is reflexive, symmetric, antisymmetric, or transitive. Then finally, you understand well ordering principle or natural numbers. So well ordering principle or natural numbers will also be captured in the next lesson. So please follow the trend as you are moving along. Now, reflexive property. So reflexive. So a relation R on set A. A relation R, so there is a symbol we use to signify relation R on set A, is said to be reflexive when A, which is a member of A, so this is a smaller letter A, which is a member of A, okay, is a reflexive of itself, okay, or it's a reflection on itself. So if I have A R A, A R A, where A is a member of this set A, then we can see that this is a reflexive relation. In order to characterize relations in mathematics, there are relation is simply how two numbers are connected. Okay, so if I have a number A, I have a number B, or even I have a number A and itself, how are these two numbers connected? That is the concept of relations. We can have less than, we can have equal to, we can have greater than, less than or equal to, greater than or equal to, and you can have A is a factor of, A is a remainder of, A is the same as. All these stuffs are order relations or relations in between two numbers. In this side, when you're talking about reflexive relationship, I want to talk about the fact that every number is an image of itself. That is the reflexive relationship. So a set A having a member A, smaller A is said to be a reflexive relationship of itself, provided A is a member of the A we are talking about. So that's the concept. So a typical example of reflexive relationship is equal to. So the equal sign here is an example of a reflexive relationship. Now, in a relation, we say that relation between two numbers can be considered as an ordered pair. So I'll have something like A comma A because this is an ordered pair. It's talking about the relationship between A and itself, and mostly reflexive relationship occurs on the diagonal. Take note of that. Diagonals, sorry. So diagonal pairs diagonal pairs are mostly reflexive relationship. Typically, you can have B comma B, you can have C comma C. These are diagonal pairs and all of them exhibit reflexive relationship. Let's talk about symmetric relationship. Symmetric relationship. What do you mean by symmetric? When do we say two numbers are connected by symmetric property? Again, a relation R on a set A. Now, I'm going to say that the members of the set is A comma B is they are members of the set A. Okay, so I've extended it. So A comma B, these are members of the set A. Now, when do we say that A and B will be symmetric? So I'll write this here: A R B, which is mapping to B R A. This relation is said to be a symmetric relation only if in any two way you go is equal. Okay, so if I have A relation B is mapping to B relation A, then This is said to be a symmetric relation if number one, you have A to be equal to B, then you have B to be equal to A, meaning that in any two way around the same relation, it should be equal. Let's see example of symmetric relation. I can have something like equal to. So A equal to B is a typical symmetric relation because when I say A is equal to B, B is also equal to A. It's perfect. Now let's consider less than or equal to. Is less than or equal to relation a symmetric relation? That is the question ask yourself. If I have 2 less than or equal to 5, right? Is this the same as 5 less than or equal to 2? No, it's not the same, right? It's not the same. So because of that, less than or equal to is not symmetric. Symmetric means that any two-way round the same relation should be equal. If I move this end, it should be equal. If I come this end, or if I reverse it, if I put B here and 2 here, it should be the same meaning. That is why it is not symmetric. Now, so there is a deficiency of what? Symmetric, right? That is what symmetric doesn't cover. Let's talk about antisymmetric. So antisymmetric. So when you talk about antisymmetric, antisymmetric is not, take note, this is very, very important. It's not opposite of symmetric. This is one thing that confuses a lot of students. Antisymmetric property is not the opposite of symmetric property. That is one thing, please take note of that. Then, what do we mean by antisymmetric? Using the same A and B, which are members of A, I'll say that a set is said to be antisymmetric. If I have A, so if I have A, R, B, mapping to B, R, A, this should be equal. This should be equal if this should be equal if A is equal to B. But take note of this condition. Only this is a relation, right? In this relation, we can only go round it when the elements are the same. So let me explain it very well here. So in antisymmetric relation, okay, this relation here will be equal only if A and B are the same. Only if A and B are the same. So I don't know if I get it. Symmetric is saying that a symmetric relation always goes 2 ways. 2 ways should be possible, right? 2 ways should be possible. Now, when you are using antisymmetric, I just want you to have a picture that antisymmetric is not the same, it's not the opposite of symmetric, in that antisymmetric is a special property talking about the fact that if a relation can be swapped, right? If I have two elements which are being connected by a relation, the two elements can be swapped only if A is equal to what? B. That gives a defined restriction that I can swap it only when they are equal. Meaning that yes, equal to is a typical example. Equal to is a typical antisymmetric relation. But now let's check something. Less than or equal to. Yes, this is a typical antisymmetric relation. Because if I have 2 less than or equal to 5, I cannot swap 2 unless they are the same. So it's true. Yes, it's true. I don't know if you're getting it. So less than or equal to here is telling us that these two relations here cannot be swapped unless they are equal because it's antisymmetric. I can have 2 is equal to 2. Yes, I can swap it. And so far as I can swap it, it's still satisfying antisymmetric. Antisymmetric is saying that you can only swap when the two of them are equal. But symmetric is saying that a symmetric relation is when the two of them goes both ways. You can have A equals to B, or swapping them always are equal. But antisymmetric is giving a restriction that you can only, right? You can only swap it when they are equal. But symmetric is just directly telling you that they should be equal. That is why less than or equal to here is not um less than or equal to here is not symmetric, but it's anti-symmetric, because anti-symmetric is a little restriction towards symmetric, so that we can only swap only when they are equal. Now let's take the third one. So we have a third example here, which is subsets. If I have two things, let's say natural numbers are subsets of what, integers, and that is true. So if I have natural numbers is a subset of integers, when I want to swap this, I would only do this only when z, which is integers, are also subset of natural numbers, which is not true. But so far as it is meeting antisymmetric rule, then it's fine. Antisymmetric is saying I can only swap when they are equal. So if they're not equal, just maintain as it is. So subsets is also antisymmetric property. Less than or equal to is antisymmetric property. Equal to is antisymmetric property. Now, the last property is what we call transitive. Transitive is so simple and direct. So if you have transitive, it means that you can have, here I have to introduce a third one. So I will say that A, comma B, comma C, which are members of the set A, with the order relation R on this set. So you realize that A, R, B going into, or comma B, R, C, then I'll say that A, R, C. So this is a relation that tells us that if I have three numbers and two of them are related, and that one of them is related to a third one, then it means that the first one will be related to the third one as well. So picture the relation as just a concept that if I have three numbers here, okay, two of them have a relationship, and the relationship is that maybe they are equal, they are not equal, or they are greater than something. But so far as there is a relation between the two numbers and one of them has a relationship with a third number, then it means that the first one will also have a relationship with that third number, and that is transitive. So equal to is a typical transitive relation, so that I can have A equals to B equal to C. It's true. I can have A less than or equal to is also a transitive relation. Okay, I can have A less than or equal to B less than or equal to C. Therefore, A is less than or equal to C. Simple. So this talks about the properties here. And if you have anything to say or any question, please put it in the comments. You can recommend for further explanation in any future videos. Thank you for being with us, and please don't forget to like, share, and subscribe.